if all that motivated us was to fill gaps in our knowledge, then we would create a tessellation around us, perfectly filled, perfectly dense understanding of the world. So what that would create is a network that has relatively high density, but could also mean that our network model has relatively high rigidity. So there aren't a lot of open spaces or undefined relations or uncertain associations that would allow for flexibility. Everything is fixed, and everything is filled. In contrast, the compression similarly, in compression progress theory, if you're always building something to make it more compressible, that will increase the density of the network. It will also increase the potential cognitive rigidity of the mental model. The benefit is that you have a less costly representation in your mind. To combat or work as an alternative to this drive for network density and sort of possibility of cognitive rigidity, the conformational change theory offers something different. For us to build networks that are conformable, that can change in their mechanical shape, we would need to build something that is not fully dense. It has to have gaps that could be squished so that we can change the shape to use it differently in a new context. That would enable less cognitive rigidity, but it would require us to have a more costly representation of the model in our minds. So how would we test these three theories that are in words and pictures? Well, again, sort of because of time, I'm not going to go through all of the details, but I did want to provide you with links to where the sort of methodological approaches are described in detail. First, for the information gap theory, we're going to use persistent homology again to identify where the gaps are and how many there are. For compression progress theory, we will use a information theoretic assessment of network compressibility that my student Chris Lynn recently published. And then in the final section, we're actually going to use mechanics and calculate conformational degrees of freedom, almost as if mental models were like proteins that could change in their shape. And we're going to test these three theories on Wikipedia data again. And this is going to be the Wikipedia data that I just described to you earlier of a single individual or a set of individuals browsing over the 21 days of the experiment. So I have three short pieces of data to show you, and then I'll sort of broaden out and talk a little bit about what I think all this means. So here's the first piece of data, testing the psychological theory of the information gap. At the top here, I'm showing you the zero-dimensional gaps, then one-dimensional, and then two-dimensional. In the color, I'm showing you the actual data from real individuals as they're browsing Wikipedia, and then in purple, in each of these plots, you're seeing the edge-rewired null model data. So here what you're seeing is that the number of gaps in 0 dimensions as a function of time rises, but it rises to a slower degree than it does in the edge-rewired null model. So what that means is that humans fill more 0-dimensional gaps than expected. You also see something very similar for the one-dimensional gaps. So humans are filling the one-dimensional gaps more than expected in the edge-rewired null model. But we see the opposite. We see a flip in 2 dimensions. So notice that the true data in blue is much higher than the edge-rewired null model. What that means is that people are allowing and actually building actively these 2-dimensional gaps at a much higher rate than we would expect if browsing was happening in a more random fashion. So why? Why is that happening? What that suggests to us is that the information gap theory is not enough to explain how humans search Wikipedia. There must be some other factor that's driving their behavior. So could it be the compression progress theory? Could that provide us with the missing explanation? Well, so here what I have is the compressibility of the network along the y-axis, and then along the x-axis is time. The actual compressibility is in red, and then in purple is the edge-rewired null model. What you can see is that humans are building highly compressible networks as they are browsing Wikipedia, much more compressible than you would expect if they were randomly moving between pages. So yes, there's evidence for compression. And there is evidence for the information gap theory as well. But both of those are going to be driving this increased network density, high clustering, very filled out network. Is that completely true, or do we see any evidence that they may also be browsing in a way that leaves gaps open for conformational change? So this is the third and final theory, the third and final data plot I wanted to show you. Along the y-axis here is the degrees of freedom, the conformational degrees of freedom of the network, and along the x-axis is time again. In the red color is the true data, and then in purple is the Edgar-Wire null model. So what you can see is that humans are building networks that have many more conformational degrees of freedom than expected in the Edgar-Wire null model. What that means is that they are building something that's flexible, that's not fully filled, that is not rigid. And so that suggests that there are maybe diverse or separate or antagonistic mechanisms that explain the curious behavior of browsing. So to put that in pictures, which of these theories have we seen evidence for? Well, we saw evidence in 0 dimensions and 1 dimensions for the information gap theory, but not in 2 dimensions. We saw evidence for compression progress, and we saw evidence for conformational change. Why have these multiple explanations and in fact antagonistic explanations present? Well, I think that an answer could be that when we are curious, we are trying to build a model of the world that balances cognitive rigidity and cognitive flexibility, and also that balances costly versus cheap mental representations. And so if we have these two drives pulling us in two different directions, then we end up building something that offers us a little bit of both. So with that, that sort of closes the 3 sections of data that I wanted to show you on testing philosophical theories, both at an individual and at the collective, and then also testing psychological theories. I want to briefly summarize what we have discussed. So first, individual and collective curiosity can be operationalized as network building processes, and these network statistics can be used to test the validity of philosophical and psychological theories of curiosity. In the first part, we found evidence for ancient philosophical styles of curiosity alive and well today in the browsing of Wikipedia. That was the busybody and the hunter. In part 2, we found evidence for Kuhn's normal science, but not for Feyerabend's characteristic-less process or Lakatos's research program, particularly because we saw evidence that the core and the periphery are not born at different times. They are both being filled out simultaneously. In part 3, we found evidence for the information gap theory, the compression progress theory, and the conformational change theory in psychology, each of which provide different cognitive affordances. But what pulls each of these studies together is this notion that curiosity is a connective practice, not only an acquisitional practice. And in order to understand it, we need to understand how ideas are being connected or related to one another. The people who were behind each of these studies is shown here. So on the left-hand side, you'll see for part 1, it was led by David Lyden Staley.